Good morning. So last class we were enjoying rational functions, and we were trying to see if we could get our heads around how to sketch them. And I gave you a set of steps on how to do it. And when I gave you the set of steps, I told you when we go to find these horizontal asymptotes that there's kind of three different scenarios we can run into. I call them case A, B, and C. And all we had done up to that point was case A. And I'd given you two problems to try and work on your own. So what I'd like to do now is go through both of those problems. And then after we go through them, I'll show you how we would handle the other cases that we could see. Sound good? Let me see here. All right, so let me get this first problem going. I was hoping I could call on some people to see if you had tried it. Let me go grab the steps. Let me grab these so we can use them. All right, here we go. All right, so I'll take volunteers first, and I'll check you off on my little list here. Anybody attempt this problem and do the first step?
I did it.
Okay, go ahead.
First step is we'll put the numerator equals 0 to find the x-intercept. So it'll be x equals 0.
And there's really nothing to do there, right? Yes. I mean, it's pretty much already solved, like x is 0. Now, Dina, what will that be in my graph? When I go to put all this, like when I get to step 4 and put everything on the graph, what is that going to be?
That'll be the x-intercept, the point where the line could go like cross.
Yeah, this is a point on the x-axis, right? It's a point on the x-axis. So just, we need to remember when we're doing these things, what each of these things represents. Dina, since that was so straightforward, did you do the second step?
Yes.
Okay, so we're finding the vertical asymptotes. You set the denominator equal to 0, right?
Yes.
And
so
when
factor.
You factor, okay.
Yes.
What
It'll
did you
be x equals 5 and x equal, the brackets is x minus 5 and then x plus 3.
Okay. Now, everyone on that step, remember that's that step that I told you everyone's kind of at a different place, but I told you the way to do it was to look at the number back here, -15, and then look at the number -2. And that's where I did that little X, and I put the -15 here and the -2 here. And then this is where you have to come up with two numbers that will multiply to be -15 and add up to be -2. And Dina is saying it's -5 and 3, which I agree. Those two numbers multiply to be -15. When you add them, you get -2. Okay, and then you set each of those equal to 0, Dina?
Yes, so it'll be x equals 5 and then x equal -3.
Good. So x equals 5, just move the 5 to the other side of the equation. Here, move the 3 over, it becomes -3, and you have two solutions. Now, what will those be on the graph, Dina?
They're going to be the vertical asymptotes, so there'll be the barriers where the graph cannot cross. It will either go up or down.
Vertical lines. Now, when I draw these, I usually draw them dotted. Like I draw like a vertical dotted line. So I'm putting a vertical dotted barrier, right? Barrier, right? And that's where when our graph is drawn, you have to go up or down, which is what Dina said. Okay, very good. All right, so how about step 3? Did somebody else do step 3? Anybody get to step 3 on this one? No. Okay. So we were trying to find the horizontal asymptotes. We want to compare the degree of the numerator and denominator. Okay, so let's see. I'll just go off, I'm just gonna go across my screen here. So Caitlin, since you look like you're ready to go there. Okay.
Because I was sick on Monday, like I'm a little bit
Oh.
because I wasn't in class.
Okay, well, look, even though you were sick, I think you can still do step 3 if I help you. Okay, so step 3, we're finding the horizontal asymptotes, and what we need to do is compare the degree of the numerator and the denominator. So Caitlin, look at the numerator. Can you now think back to polynomials? Remember, the degree was the highest power of x, right?
Yeah.
So what is the degree of the numerator?
Oh, just like 1.
1. Okay, so the degree of the numerator is 1. Okay, what's the degree of the denominator?
2.
Caitlin? 2. So the denominator's degree is 2. The numerator's degree is 1. So what we do for step 3 is we figure out what the 2 degrees are. And then last class, I gave everybody this, and we still need to talk about this. So, I don't know if that's going to work. Try it. Okay, so Caitlin, what I said to the class last time is that when we look at the 2 degrees, the numerator and denominator, we can have 3 different things happen. First case I called case A is if the numerator's degree is less than the denominator. Okay. The second case is if the numerator's degree is bigger than the denominator. And then the last case is if they're the same. So all we did last class was case A. So I had sent everyone home with the 2 problems that were both case A. So Caitlin, can you see that your numerator's degree is smaller than denominator?
Yeah.
Okay, so if that happens, then your x-axis will be your horizontal asymptote. Now, maybe you're not sure what a horizontal asymptote is at this time, but just following this, we know right now the x-axis is our horizontal asymptote. Now, can somebody help Caitlin in kind of describing what a horizontal asymptote looks like on our graph, like what it is, or what I described it as? Anybody? No? No, I'm all alone here today. So this is a horizontal. I called it a magnet, okay, right? That pulls graph toward it at the ends only. Now, Caitlin, you're probably like, what the hell is he talking about? Just hang tight, okay? And also remember that anyone that may have missed class last time or were sick, I have the lecture from last time up on YouTube. Just go to Canvas and you can review it. Okay, so that's step 3. Now, step 4 is to basically get all the information we got from steps 1, 2, and 3 and put them all on a graph. So now we start trying to put the graph together. So I'm going to draw my X and Y axes here. And I'm going to draw the graph in green. Okay, so starting with the first step, we have an X-intercept, which is an actual point that's on our graph, and it's at X equals 0, and it's on the X-axis. So that's right here. I know that that point belongs to my graph for sure. The next thing I know from step 2 is that I have 2 vertical dotted barriers that I need to draw at X equals 5 and -3. So these are not part of the graph. They are just to help you draw the graph. So I'm going to go to 5 and -3, and I'm just kind of eyeballing just about where those numbers are. And I'm going to draw vertical dotted lines. And again, these are not part of my graph. They're just going to help me draw the graph. And I just have to remember when I draw the graph, those barriers are going to force my graph to either go up or down. All right, the next thing I know is that the third step told me that I have a horizontal asymptote, which is the x-axis. but it's only at the ends, okay? It's at the ends only. So what I'm gonna do is on the left end, on the x-axis, I'm gonna extend it with a dotted line. And on the right end, I'm gonna extend it with a dotted line. I'm just gonna remember that these dotted lines are gonna act like magnets and they're gonna pull the graph towards it as I try and draw the graph. So that's all steps 1, 2, and 3 put on a piece of paper. Any questions on that? The next step is to pick test points. Now, this was the confusing part, okay? How do we pick test points? What are test points? So the whole idea here is what we have right now is not enough to draw the graph. We need more information. So we need to come up with these things called test points. And the test points, you're always going to have, do y'all remember what I said, how many test points you'll have?
One more, the total of X-intercept and the vertical barriers.
Very good. Dina said, you'll always have one more test point, then you have the total of X-intercepts and vertical asymptotes. So I have one X-intercept, I have 2 vertical asymptotes. That's 3 things I have, right? So I need 4 test points in order to draw this accurately. My test points have to be to the left of the first vertical asymptote. I need to pick any point over here. So I'm gonna pick -4. I'm gonna circle it, okay? And notice I didn't put a dot here. I put a little X because I don't want you to think this is part of the graph. This is just me saying, I'm gonna pick a point over here. And then I'm gonna pick another point between here and here. So how about something like, I don't know, -1? Something between this and that. So I don't know, I'll go with 4. You can pick any point you want between here. You could have picked 1, 2, 3, 4. You could have picked a fraction, although I don't recommend it. Let's see, over here I'm gonna pick, let's go with 7. And then what you're gonna do is for each of these test points, unfortunately, you have to plug each of these into the original function. And all you're looking for is whether or not you get a positive or negative answer. So that, again, this part sucks, but you have to do it. You have to plug -4 into the original function, plug -1 into the original function, plug 4 into the original function, and plug 7 into the original function. Now the original function's up here, so let me go grab it. Bring it down here. So we've done this before in the past. If you're given a function and you're asked to evaluate it, all you're doing is replacing all your x's with these numbers. So I'll do the first one. At -4, I get -4 over. Okay, I have to do -4 squared minus 2 times -4 minus 15. So this gives me -4 over, let's see, -4 squared is 16. -2 times -4 is 8. So I get 16 plus 8 minus 15, which gives me -4 over, let's see, I think that's 9. And I told y'all last time, we don't care about the exact value. All I really care about is that this is a negative number. It's negative because we have a negative divided by a positive, that's negative. And we have to do the same thing for all the other numbers, okay? So if we do -1 now, I'll go a little faster on this one. -1, we plug in -1, we'll get 1 plus 2 minus 15. You get -1 over, what's that, 3, -12. And then a negative over a negative is positive. So now that'll be a positive number. If you plug in 4, you get 4 over 16 minus 8 minus 15. You should get 4 over, I think it's -7. You'll get a negative number here. And then the last one, you plug in 7, so you get 7 over 49 minus 14 minus 15. This is going to turn out to be a positive number. So students will always ask me this, okay? They'll always say, if I just get the first one, can I just assume that the rest of them will just switch? So like, if I get the first one's negative, can I be sure that it's going to go negative, positive, negative, positive? Or do I have to test each point? And unfortunately, you have to test each point, okay? You have to, because it could have gone like negative, negative, positive, negative. You can't tell. All right, any questions on that step? what do we do with this? Well, we say, all right, at -4, I have a negative number. So that means if I go now, this point is going to be on the graph. If I go to -4, I need to draw a point that's down somewhere, negative, but I don't care where, just put a point somewhere. And then at -1, I need a positive number, which will be above the x-axis. So I go to -1, I just put a point somewhere up here. If you want to put it up here, you can. You want to put it right here, you can. It just needs to be above the x-axis, that's all. And then at 4, I have a negative number, so I can put that wherever I want. I'll put it here. And then at 7, I have a positive number, so it goes here. Any questions on that step? Caitlin, is this making sense? Okay. All right, now put it all together. It's time to draw the picture. So the way that I like to draw the picture is I always start at the very leftmost point I have, which is this blue one right here. And I just imagine that I have to draw this with a nice smooth curve. I need to draw it out to the left and to the right. So let's see here. Juliet, are you there?
Yes.
Are you with me right now?
Yeah.
Okay, so if I asked you right now to draw this, I have this point right here, and I ask you to draw it out to the left, what do you have to do when you draw it?
When you draw it, because the horizontal asymptote, like, isn't it gonna go like towards it?
Exactly. That horizontal asymptote is a magnet. It pulls your graph towards it. So when you draw it to the left, you just have to draw a graph that goes up towards it, right? Now don't cross through, just draw it getting closer and closer, and that's sufficient, just like that. Okay, good, Juliet. How about to the right? If I were to tell you, start drawing to the right, what has to happen?
Then it has to cross through that, yeah, -3 line.
So this dotted line, Juliet, that dotted line is our vertical asymptote, right?
Yeah.
And a vertical asymptote is a vertical dotted barrier. So that is a barrier, Juliet, and you're
Oh,
not allowed to cross that. What it does, though, is it forces you to either have to draw your graph up or down, getting closer to it. So, Juliet, am I going to draw this graph going up, closer to it, or am I going to draw it going down?
Okay, no, it's gonna go down.
It's got to go down. Now, it has to go down. Imagine this dotted line extends. That's fine. Just draw this. This is correct, but it's not because, I told you this last time, it's not because it looks like it goes down. It's because if you were to have drawn it going up like this, then you would have created an x-intercept that does not exist. The only x-intercept we have in this entire graph is right here. So if you go up, you're doing something that we already know isn't supposed to happen. So it's like a process of elimination. You're saying you can't go up, right? So you have to go down. Good. How about Katrina? Are you here, Katrina?
Yes.
Where the heck are you on here? Oh, there you are. Okay. All right, is this making sense, Katrina?
I think so, yes.
Okay, so you get the next section. Once you get to a vertical asymptote, you have to pick up your pencil and you have to go to the next point that you have, which is this one right here. So tell me, Katrina, to the left, if I try and draw this to the left from this point, what's going to happen?
It has to go up.
Has to go up because the vertical barrier, right? Can't go down because you'll make an x-intercept, right? So let me draw that for you. It's going to go like that. Oh, do it in green. So it's going to go up like this. Okay. Now, how about to the right? What has to happen?
It has to go through the x-intercept
Yep, it has to go to here. And then where?
to the bottom 4.
To this point. So you're just like back in kindergarten, connecting dots, right, at this point. And then keep going to the right. And what has to happen?
It has to go down.
Has to go down. Like that. Very good. You want to do the last point? Tell me what happens to the left and to the right.
It has to go up
Has to go up. And to the right.
and then down. But not the-
Down towards the horizontal, right? Like this. That's it. Okay, that would give you perfect score on the test if you could put that together. All the little details of exactly what it looks like are not important. What's important is, do you have this magnet? Do you drop down forever like this? In here, do you go up, you know, do you go up right here and go down right here, cross through here? Here, do you go up and then flatten out to the horizontal? As long as all those characteristics are on your picture, you're good. Here's what I won't accept, okay, on the test. I'm gonna show you something. See if I can find it, hold on. See if I can bring this up. I haven't used this in a while. Oh, here we go. What was it? Was it x squared minus 2x? What was the original function?
The bottom one was x squared minus 2x minus 15.
Minus 15, okay. Thank you. Okay. Now, I've had students do this before. Can you all see that calculator? I have had students do this before because they have graphing calculators that they used in high school or something. And so they'll go and they'll turn this in, like they'll just draw this picture. They'll be like, that. That's what they will submit for the test. And that I won't give you any credit. This is not about using a graphing calculator to do this. It's about, can you follow a process, a procedure? All right. Are we clear on that? So, you know, I may have mentioned this earlier in this class. This is not about doing graphing rational functions. This is not about that there's ever going to be a point in your life where you're going to have to graph a rational function. Most of you will never have to graph a rational function, okay? Or do really anything that we're doing in here. This is really about, can you follow a procedure, okay? To me, that's what it's about. Can you learn a procedure and execute the procedure? Yes, there's little algebra things you have to know, but it's more about, do you have the ability to learn a set of steps and follow those steps? Because that will be important to you in your future, you know, job or whatever you're going to do, your career, is you want to be teachable. You want to be someone who can learn something and then execute it. I always think about it like first time you ever use a copying machine. You know, it's like the first time you ever use a copying machine, you have to figure out what you need to press and, you know, and then you make your copies. Right? You learn it. And then after that, hopefully someone doesn't have to show you each time, right? Like you just pick it up and then you go. Employers are looking for people who can learn and not people that have to continually reteach. So to me, this is just about learning procedure. I hope that makes sense. It's not about the rational function. All right, here we go. We got the next one. So we're going to follow the steps again here. This one's more complicated, all right? So let's go through step one. I'm going to find the X-intercepts. And to do that, I'm going to set the numerator equal to 0. Now, I'm going to work faster through this one, all right, because I want us to be able to get on to some other examples. To do this, I'm going to factor. So I have to find two numbers that multiply to be -21 and add up to be -4. And I believe -7 and 3 are going to work there. So I put -7 plus 3 equals 0. And if I set both of these equal to 0, I get 7 as an answer, and I'll get -3 here. Any questions on that step? Everybody feel like they could do that if they had to? Step 2, we set the denominator to 0. So I take x cubed minus 3x squared, I set it to 0. Now in this one, I have to factor out a greatest common factor, right? Because it's not a quadratic like this. So I pull out an x squared, and I'm left with x minus 3. And now I set each of these equal to 0. So x squared equals 0, and x minus 3 equals 0. And let's see, Bonnie, is Bonnie here today? I don't see Bonnie today. How about Darshil? Are you here?
Yes, I'm here, but I have a very noisy background.
It's okay. We'll be brief. Can you tell me what the two solutions are for this, for these two equations? So what number squared gives you 0? And then what would this be?
0 and then a positive 3.
0 and positive 3. Good. Okay. Good. All right. We're getting there. So right now we have 2 X-intercepts. We have 2 vertical asymptotes. Right away, right now, you know you're going to need 5 test points because you have 2 X-intercepts and 2 verticals. But we're not at that step yet. But I'm just kind of pointing out, at this point, you know how many test points you need. The next thing is to find the horizontal asymptotes. So let's see here. Lily, are you here, Lily? Yeah, Lily's here. Are you here, Lily?
You said Lily, didn't you?
Yes, I did say
I'm
Lily.
sorry.
Yes. It's okay.
Um,
Lily, I'm looking for step 3, finding the horizontal asymptotes. I need you to compare the degree of the numerator and denominator together. So what is the degree of the numerator?
the degree of the numerator is 2,
Okay, degree of denominator?
3.
3. Okay, so the degree of the numerator is smaller than the denominator, right?
Mm-hmm.
Which is again case A, right? These are the cases I gave us last time.
Mm-hmm.
We haven't done anything else, so it's going to be the same result that we had before, that the x-axis is the horizontal asymptote. Agree, understand?
Yes.
Okay. Okay, because we're doing case A. All right, we're ready to put everything on a picture now. We'll stick with Lily here for a minute. Lily, let's start putting things on the graph. So we start with our x-intercept. So what am I going to draw on my graph given this information that we found? What am I going to put here?
Here's where you start to lose me. Do you just plot the points?
Yep. For the x-intercepts, we're just going to plot these points on the x-axis.
Okay.
So we just go out to 7, right? And we put a point. We go to -3 and we put a point. Is that clear?
Mm-hmm.
Okay, so now Lily, let's look at step 2. These are vertical asymptotes. So these are not points. These are your vertical dotted lines, right?
Mm-hmm.
So I have 2 of them at 0 and 3. I'm going to start with 3 first. So at 3, I draw a dotted vertical line that's going to act like a barrier. And then where else do I need a vertical dotted line, Lily?
At 0?
At 0, but that's kind of hard to draw, isn't it? To draw a dotted line on top of a solid line like that. You'll see it, but you can't really see it. So in the past, what my students have done is they've drawn that dotted line kind of at little like dashes angled a little bit so you can see it. That makes sense?
Mm-hmm.
That way it shows up that you can see you have 2 verticals. All right, last thing, Lily, we need a horizontal asymptote, and we discovered that it was the x-axis because we were looking at case A. So what am I going to draw here?
you're gonna do the horizontal asymptotes, so they'd go on 2 and 3? Question mark.
Not at 2 and 3. This just tells us where it is. If this is smaller than this, then you're always going to have a horizontal on the x-axis.
Mm-hmm.
Okay, so these numbers don't really factor in other than telling us that it's this case. So since it's the x-axis, we'll do what we did before. Just to the left of the x-axis, I'll draw a dotted line. To the right of the x-axis, I'll draw a dotted line. And those are my magnets. Every single time the numerator's degree is smaller than the denominator, you're always going to have this picture. Okay?
Got it.
Okay. All right, now we need test points. So let's see. Cheyenne, are you here? Okay, Diane?
Yes.
Hey, how's it going? You're multitasking.
Sort of.
I appreciate you having your camera on at least. Okay, so I need test points. So can you tell me where my test points should be here? Or you get to pick them. You have flexibility here. We'll need 4 of them. I mean, sorry, 5 of them. So what test points would you like to use? Do you know what I'm referring to?
Negative. Yeah. Wait, so I don't know, like -4 and
Okay, -4. I'm put a little X here, -4. Good. I like that one. That'll tell us everything to the left of this dot.
yes, -1.
-1 will work. Good, because that's something between this dot and this vertical will have some information. Good, you're doing good. Keep going.
2, positive
2, okay, 2 will work. That'll give us some information about what's happening between these two. 2 more.
I guess 5
5, good. 1 more.
and I guess 8.
8, okay. And so what we're going to do now, and again, this is the part that I think sucks, is you've got to plug all these values into the original function now. So you've got to evaluate the original function at -4, evaluate the original function at -1, evaluate at 2, evaluate at 5, evaluate at 8. All right. Here we go. There's the original function. I'm going to do one of these. I don't think I'm going to do them all because, I mean, I'll tell you what the answers are, but I'm not going to like go through the detail. So when I plug in -4, I'm going to have -4 squared minus 4 times -4 minus 21 all over -4 cubed minus 3 times -4 squared. So that's a lot to have to figure out here. This is 16. -4 is 16 again, so plus 16 minus 21 all over -4 times -4 times -4 is -64. And then we have to do -4 squared is 16, but then times -3. What's that? -48, I believe. So we should get a positive number on top and a negative on the bottom, which gives us a negative number. This is an important step. Does anybody have a question on this? Because if you get these wrong, it's going to throw everything off.
I don't have a question about the steps, but on the test, will we have to write everything out, or are we able to do it on our calculator and just put like negative or positive?
Oh, you can, yeah, you can just get negative, positive. You don't have to. Now, I do want you to do all this work, but for the test points, just do it on your calculator. It's fine. Just make sure that you do it correctly, because it's wrong, right? So here's what's going to happen. All right. I'm going to just fill in the rest of this. It's going to be positive. And then let me just make sure. It's going to stay positive. Then it's going to go negative, and then it's going to go positive. I'll check it when I'll graph this on the computer in a second, but we should have negative, positive, positive, no switch here, then negative, positive. So now in green, I'm going to put my points. At -4, I should be in negative, so I should be down here somewhere. At -1, I should be positive, so I'm going to put a point somewhere on the top. At 2, another positive, I'll just put it here. And then at 5, a negative, so down. And then at 8, a positive, like that. I'm ready to draw. Starting at the leftmost point, let's see. Evelyn, is Evelyn here? No. How about Elisa?
I'm here.
Are you following this?
Yes.
Okay. So I always recommend you start at the leftmost point, which would be this one, and then just start drawing out to the left and then to the right. So to the left, what has to happen, Elisa?
It has to go towards the horizontal asymptote.
Okay, very good, like that. Now, how about to the right?
I want to say that you connect it.
Yeah, connect it. And then keep going.
Yes.
Connect again.
Yes.
And then, uh-oh, you have a barrier.
And then you just go up.
You got to go up. Good. Now, what's the next point, Elisa? What's the next point we need to look at? We've done all this. Go ahead.
2?
Yeah, the one at 2, right? Right here. So, Elisa, carefully, tell me what happens to the left. If I draw it to the left.
You just have to draw it towards the line.
Up or down?
Up.
Up. How about to the right? How do I draw it?
I want to say you also do it up.
You do. You go up again because you can't go down. And this again is that critical thing. If we were to go down, we would cross the x-axis. We don't have any x-intercepts here. We didn't have any x-intercepts anywhere between here and here. So it's not a very good drawing. Goes through like this and goes up like that. It almost looks like a little parabola in here. It's not a parabola, but that's kind of what it looks like. Good. You're doing good, Elisa. How about the next point? It's this one right here, 5. So to the left, what happens?
It's gonna go down.
Got to go down. So I'm gonna just make it go down like that. This thing continues like that. And then to the right.
And then you connect it to the next 2 points and do it towards the horizontal asymptote.
Perfect. There it is. Good job. All right, that was really good. Let's check it. I'm going to go to some graphing software here. Let's see, x squared minus 4x minus 21, x squared minus 4x minus 21 over x cubed minus 3x squared, I think it was. Yeah. Okay, so here's the graph. From the computer, here's the graph. Oops. That's what it has here for us, right? Is that what ours looks like? Kind of. What about this U here? It's kind of missing. Let's see. Let me zoom out. Ah, there it is. See? So it's hard to tell from this picture. It's hard to tell what's going on But from our picture, we can really see that like at -3 here, we can really see on our picture at -3, it's below the x-axis. And it flattens out and then it goes up. There's the U and then does the same thing over here. Yeah, we're good. All right, how are y'all feeling about this? I mean, I understand this is not the most fun thing to do, graphing rational functions. So are there any questions right now? I'm going to give us a new problem that's not going to be case A now. I have to show you what happens in these other cases. So I think it's time for that. So let's go about doing this problem. Let's sketch f of x equals 3x squared minus 9x over x squared. Let me think about this. Hold on. I'm making this problem up, so I need to make sure it works the way I want it to work. You know what? Let me change one thing to make this work a little better. Let's make that 12x on top. Yeah, and then on the bottom, let's go x squared minus 4 there. So we have a rational function here. We're going to go try and graph it. We're going to try and use the steps and see how this goes. All right, so first step, X-intercepts, I set the top to 0. If I set the top to 0, I can factor a greatest common factor out. 3x can come out. I'm left with x minus 4. And then I set each of these equal to 0, and I get two solutions, 0 and 4. So I'm not like showing that little step, but I'm assuming you can get this. Step 2 is going to be the vertical asymptote, so I set the denominator equal to 0. Everyone here should recognize this as a difference of squares, right, Bela?
Right.
Right, okay, so that's a difference of squares. Are you just being agreeable, Bela, or do you see that now? I know we were talking about that the other day.
Yeah, no, I think I understand it a little bit more today.
Okay. So we have two X-intercepts. We have two vertical asymptotes. Any questions there? Third step, and here's where things are going to be changing. So we want to do the horizontal asymptotes. We're going to compare the degree of the numerator and denominator. So the degree of the numerator is equal to 2, the highest power of x, and the degree of the denominator is also equal to 2. This is the first time this has happened. We have the same degree. So now I need to go grab those steps so I can show you what you do in the event that you have the same degree. Whoa. Okay, so we don't have case A here. They're not equal. I mean, sorry, the numerator is not smaller than the denominator. They're equal. The numerator is not bigger than the denominator, right? They're equal. And in the notes, I said, then what happens, right? And I left ... and I didn't tell you, okay? So now I'm going to tell you what happens when this happens, when they are equal. And this always confuses students, all right? When they're equal, what you do is you look at the leading coefficients. So you look at the 3x squared here, the 3 there. You see that 3 in front? You're going to take that number and you're going to divide that number by the number in front of the x squared on the bottom, which is a 1. So your horizontal asymptote in this case, this is case C that we're looking at, your horizontal asymptote will be equal to the 3 divided by 1. 3 divided by 1 is 3. This is your horizontal asymptote. Now, I will help you when we go to graph it. I'll show you where that's going to be on your graph. So again, I can't stress this enough. If the degrees are equal, you're actually going to look at the numbers in front of those powers of x, 3 over 1. That's the only time you ever look at these numbers, is when these degrees are the same. If the degree on top is smaller than the bottom, then we know it's the x-axis. That's what we did a bunch of problems like that. It's only when they're equal that we look at the numbers in front. Okay, I'm ready to draw this. Do I have any questions? My graph is going to be in green. Starting with the x-intercepts, I have them at 0 and 4. 0 and 4. I have points on my graph. I have 2 vertical asymptotes, one at -2 and one at +2. Those are vertical dotted lines. And now's the new thing. The horizontal asymptote is 3. What that means is you have a horizontal line, dotted line, but instead of it being on the x-axis, it's moved up 3 spaces up. So if I were to look at my graph, maybe 3 is about right here. I don't know, maybe it's not there. Maybe 3 is about right here. Okay, there's 3. What I'm going to do is the horizontal asymptote tells you about the end behavior only. So I am not going to draw a line all the way across. I'm only going to go out to the left and draw a dotted line out here. That's my magnet at the end. And then on the other side out here, I'm going to draw my dotted line. See, I did not draw it all the way through the middle because the horizontal asymptote only tells you about end behavior. Okay, do not draw this all the way across because it's going to confuse you if you do it. You'll have a dotted line, you'll think you can't cross it. You can only the verticals you can't cross. This dotted line, horizontal ones only tell you about the ends. So what happens in the middle, there's a lot of things that can happen. All right. I always know when students don't listen to me on this because when they do their test, they draw a dotted line all the way across, which means they probably went to a tutor or someone else because most of the time tutors are going to draw it all the way across. All right, most of the time. It's dangerous. So only draw it at the edges. Questions on that? All right, here's what I'd like for you to do. I'm going to give you 5 minutes. Let's go 10 minutes. I'm going to give you 10 minutes to see if you can complete this problem. That means you have to come up with the test points. You have to plug those test points into the original function. I'll put the function down here for you. There's the function. All right, let me erase that. Erase that. Put that back in here. This was a 3 and this was just x squared. So figure out what your test points are, plug them into your function and put your points on there and see if you can draw it yourself. And then I'm going to call on people. I'm going to reshuffle everybody again. I'm going to call it on somebody. And maybe you'll be the unlucky one. And if you don't have it, you don't have it. But I want everyone trying. So 9 minutes. Okay, I'm thinking we're getting close on time here. Does anyone need more time? All right. Okay, we'll start with Bela. I don't think I've called on Bela.
I don't think you have either.
Okay, Bela. So did you get test points?
I didn't figure all of them out. This
What did
step,
you pick? What did you pick for your test points?
well, I only got through a few of them. I'm not very confident in this part.
Okay, well, tell me what you picked, because you first have to start by picking them so before you plug them into the function. So what values of X did you pick? So did you pick something over here?
I have one of them over there, yeah.
Okay, what did you pick? What number?
4, -4.
-4. Okay, that'll work. All right. Did you pick something in here?
I put down -1.
-1. Okay, good. How about here?
1.
Okay. How about here?
And 3.
3. Okay, we need one more over here.
5.
5. Okay, so now these get plugged in. Did anybody pick anything different than this? Did someone do -3 instead of -4?
I did -3.
Yeah, I mean, it doesn't matter. I mean, we should all get the same answers in terms of if it's positive or negative. So we've got to plug these in to our original function. 5 things. It's going to suck. Now, Bela, had you tried plugging one of these in at all or no?
I started on number 4, but number 4. Sorry, I started on f of -4, but I didn't fully finish that one yet. I'm kind of scared of this step.
Okay, well, let's go through it. Let's write it out first. It's 3, and then you have the -4 that has to be squared minus the 12 times the -4 over the -4 that has to be squared and then -4. Is that okay? Just replacing all your x's with -4s?
Mhm.
Okay, so let's start squaring things first. What is -4 squared?
16.
16. So this is going to be 3 times 16. And then here we have to multiply these together. You have a -12 times a -4. 2 negatives multiply to be positive, so we can go plus, and 12 times 4 is 48. Is that all right?
Yes.
Okay, on the bottom, the -4 squared was 16, and then -4. That's okay?
Yes.
Okay, 3 times 16, Bela, that's a positive number, isn't it?
It is. 3 times 16 actually comes out to 48.
48, and if you add 48 to 48, you'll have a positive number on top, won't you?
Mm-hmm.
And on the bottom, if you do 16 take away 4, you're still going to have a positive number, right?
Right.
So a positive divided by a positive should also give you a positive, yes?
Yes.
Okay, so that's all we need to know, right? That's it. So that's done. Now we do the same thing for each of the other ones. So does somebody else want to tell me what they got as far as positive or negative for any of these? Let me see. Who have I not talked to? Diane, we talked to. So I think I've gotten through everyone pretty much. So volunteer to tell me that what the next 2 of these they got? Positive or negative? Please, not all at one time. I don't like people when they're talking over each other. Come on.
The next one is negative,
Okay, negative, and then
positive,
positive. Okay. Just go ahead and finish it up. Negative and
Negative.
positive again?
yes.
Okay, good. That's right. Now, Bela, do you feel like if you plug these numbers in, you understand the process a little bit? Just kind of take your time through it?
Yeah, I think the part that's gets into my head is that you kind of can pick whatever points, like how you said, like, did somebody use a different point?
Mhm.
It's like a lot of leniency for something that's supposed to be kind of strict.
Yeah, it's just because we're trying to see, when we pick like -4, you pick -4, all we're trying to figure out is if this point is above or below. So here I'd get a point above, right? That's what we're gonna get because it's positive. If somebody else like Dina picked -3, she's also gonna have a point above, right? That doesn't change the way we would draw it. To the left, we still have to go to the magnet, and to the right, we have to turn up. It doesn't matter if your point's here like this and turn up, because the vertical barrier, you can't cross the x-axis. That would be the same general picture as you having your point here. You would still have to go here and you would still have to turn up. Do you see? It doesn't really change. It changes subtly, it changes, but we still have the general behavior. It goes, flattens out to the left and it goes up to the right. That's all we need to know for this class. If this were a calculus class, we would want more detail, but here we're just general shape. Does that
Okay.
kind of settle your mind a little bit?
Yeah, it makes a little more sense.
Okay. So we put a point above here, we put a point below here, we put a point above here, a point below, and then a point above. And now we connect all the dots together. So I'm going to do this kind of fast. The first dot to the left flattens out towards it. To the right, I have to turn up. Then I go to my next dot here. To the left, I have to go down because of the vertical. Kindergarten, connect dots, connect dots. To the right, have to go up. Go to the next dot. To the left, I have to go down. Connect, connect, flatten out. And we're done. Well, what do you think? It's a lot going on here, right? With these, a lot of things to keep track of. Okay, so what do y'all think? Do you think I should give you one to practice right now on your own? Take it from the beginning to the end, or do you just want to move on to the next idea? What do y'all want? Practice or move on? Should I give you a poll? I'll give you a poll. That way you can tell me. Practice one more, yes. Move on, no.
I said practice another one so I can rewatch this video.
No. Right now it's almost 50-50 on. Yeah, so y'all are pretty much like 50-50. Half of you want to move on, half of you want to practice another one. So here's what we'll do. We'll let's move on, and then at the end I'll have a problem that set of problems for you to practice. All right, let's do that. Okay, so you know how I said that there was case A, B, and C, right? Case A, B, and C. We've done case A, done a couple of those. I've done one problem like case C. I am not going to do case B, right? So you're not going to be tested on this at all. So all you're ever going to see on your test is numerator less than denominator or numerator equal to denominator. That's all we're going to do. We're going to move on to the next topic, which is a completely new graph of a completely new function. All right, so we're gonna end it for rational functions for now. Well, for now, until we talk about them for the review for the final, which is a week from today. So let's do this. I want to give everyone a break. Let's do a 10-minute break, and then we'll come back and we'll start exponential and logarithmic functions. All right. So 10 minutes. I'll put a clock up here for everyone. All right, there we go. We'll be back in 10 minutes. Okay, everyone, let's get back to work here. So what we've done so far in the class in terms of functions is we've looked at lines. So we've looked at linear functions. We've looked at quadratic. We've looked at polynomials. We've now done rational functions. And like I stated before, each one of these kind of serves a purpose in the real world. You know, linear functions are good for certain things, quadratic for something else, polynomials for something else, and rational for something else. Those are what we've done, okay? We should all be able to graph, sketch those types of functions if I ask you to. Now, the next function we're going to talk about are called exponential functions. So what I want to do is kind of motivate this with an idea before we actually get into the definition. So I want us to take a look at a function. All right, here's a function f of x equals, let's say, 2x. This is a linear function. We know it's linear because we have x raised to the first power. So we know if we graph this, it looks like a line. But what I'd like for you to do is think about like kind of the old school way we used to get points on a graph. We do this thing called a t-table, where here you plug in x, and then here is what the function spits out. So like, for example, if I plug in, let's say 0 into this function, 2 times 0 would give me 0. So that would be a point on the graph, 0, 0. 0 goes in, 0 comes out. If I plug in 1, then I go 2 times 1, that's 2. So that gives me a point 1, 2. If I plug in 2, 2 times 2, that would give me 4. So we have the point 2, 4. I'll do 2 more of these. 3, 2 times 3 is 6. So we get the point 3, 6. Let's do, I'll just go a little further. How about 7? 2 times 7, that would give you 14. So 7, 14 would be on the graph. And if we plotted all these points, we would get a straight line. Okay, so if we did this plot, that's not very good. Let me do it this way. If we plotted these, 0, 0 would go here. 1, 2 would go here. 2, 4 would go here. 3, 6 would go here. And then if we connect them all together, we would get our straight line. Okay. So the function 2x looks like this, right? And this is what the table, we call this a t-table. A t-table. The t-table for that looks like this. So what I'm going to do now is I want you to try and think about a new function, okay? But I'm not going to tell you what it is. It's some new function. I'm not going to tell you what it is, but I'm going to show you its t-table. Okay, and here's what the t-table looks like. You plug in a number and it spits out something. So here's what I'm going to tell you. When you plug in 0, you get 1. When you plug in 1, you get 2. When you plug in 2, you get 4. When you plug in 3, you get 8. When you plug in 4, you get 16. I'll do one more. When you plug in 5, you get 32. So can somebody tell me if they see a pattern in what is happening here? Maybe if someone can tell me what we would get if we plug in 6, what does it look like we would get? Does anyone see the pattern?
64.
64. So what pattern do you see here?
You multiply each number by 2.
it looks like we're doubling each time, right? Do y'all see that? Every time you jump, you're multiplying by 2. Jump here, 2 times 2 is 4. Take 4, multiply by 2, you get an 8. Multiply that by 2, you get 16. Multiply that by 2, you get 32. Multiply that by 2, you get 64. Understand? Well, that's great. That's great. But now let me ask you this. What would you get if you plug 13 in? So right now, I think the only way that you could do this is to figure out what happens when you plug in 7 first, right? What would happen if you plug in 7? You have to double 64, right? And what do you get when you double 64?
128.
128, right? And then you could figure out what happens at 8, and then 9, and then 10, and then 11, 12, and 13. You'd have to build your way out to 13. Do y'all see that? So that's tedious. It would be better if we actually had a function that when I plug those numbers in, these numbers here, when I plug those in, that function would spit out those answers. The question is, what's the function, right? Because this is not a linear function. Notice that when I plug in these numbers, there's not an easy way to see how 1 becomes 2 or 2 becomes 4. Well, does it look like I'm doubling the answer? Look, if I take in 1 and I double it, I get 2, don't I? If I take in 2 and double it, I get 4, right? 2 times 2 is 4. But what about 3? What happens when you double 3? You should get 6, shouldn't you? But you're not, you're getting 8. If you take 4 and double it, you don't get 16. When you take 5 and double it, you don't get 32. So it's not like this function where you're just doubling what goes in, right? 2 times 2 is 4, 2 times 3 is 6, 2 times 7 is 14. There's something different happening here. Do y'all see that? It's something very different than what we've seen before with a linear function. It's also not quadratic, right? In terms of we're not squaring these numbers, right? 1 squared is not 2. 2 squared is 4, but 3 squared is not 8. 3 squared is 9. 4 squared is 16, but 5 squared is not 32. 5 squared is 25. So it's not, we're not doubling it and we're not squaring it. It's something different. And it turns out that it's what we call an exponential function. So let me show you what the function is, all right? This is the function. The function is f of x equals 2 raised to the x power. 2 raised to the x, not x squared, okay? Not x squared, 2 raised to the x. So what you have here is this number right here is called the base, and this right here is called the exponent. And in all of the problems we've done, everything we've done, all the graphs that we've done in this class up to this point, linear, quadratic, polynomials, rational, if you look back at all of those examples, x was always on the bottom, and it was always x to a power. It was never the other way around. It was never a number on the bottom and x as the power. And that's what makes an exponential function exponential. So let me show you why this works. If I make that t-table again, here's x, here's f of x. If I plug in 0, that's 2 raised to the 0. And if you do that on your calculator, 2 raised to the 0, you should get 1. By the way, I should point out that for exponential functions, everyone will have to have their calculator ready to go, because there's no way to do these easily. Well, as we get to harder problems, there's no way to do it in your head. You have to have a calculator. So everyone's going to need to know where their little raised key is. So I encourage you to practice here. If we plug in 1, 2 to the 1, that's 2. If we plug in 2, 2 squared, that's 4. We plug in 3, 2 raised to the 3rd, that means 2 times 2 times 2, that's 8. And you can see, hopefully, that these are matching. 1, 1, 2, 2, 4, 4, 8, 8. The next one, if we plug in 4, be 2 to the 4, which is 16. Right, so this is an example of an exponential function. It's a number raised to the power of x. So let me show you an example. I'm going to show you a physical example of where this might, just so I can show you it, like this exponential thing happening with a visual example. So right now I have a piece of paper, right? Y'all can see my video. I'm going to make a t-table. Okay, and what I'm going to have here is on the left side, this is going to be the number of folds I have in the paper. And this is going to be the number of rectangles that you see. So right now I have not folded this paper, right? I have not folded it. So there are 0 folds in the paper. How many rectangles do you see?
Just one.
Just one. Okay, now I'm going to fold it, all right, one time. And where I folded it, to make it easier for you, hopefully, where I folded it, I'm going to draw a line so that you can see the fold. Okay, so I folded it in half, all right, and now how many rectangles do you see here?
2.
One fold, got 2 rectangles. Now I'm going to fold it like I did before. That's my first fold. Now I'm going to fold it in half again. When I open this up, how many rectangles will there be?
4.
4. Okay, so let me draw it again so you can see. 4 rectangles, right? So when I folded it twice, there are 4. Let me do it again. 1 fold, 2 folds, 3rd fold. When I open this up, how many will there be? 6, 8, 100, I don't know. Let's see. I don't know if you can see that, but we have 4 across the top, 4 across the bottom. So now we have 8. So 3 folds gave me 8. Let's go again. 4 folds, what do you think? Here's the 4th fold. How many rectangles are we going to see? What do you think?
16.
16? Let's see. It gets hard to draw all the lines here, but I have 1, 2, 3, 4 across the top and 4 down the side. So 4 times 4, there's 16 rectangles in here. If I did it one more time, I should expect to see 32. It's doubling each time, right? That's what's happening. That's exactly what that exponential function we just looked at was doing. Hard to see this, but I have 8 across the top and I have 4 down the side. So that's 32. So 5 folds was 32. So this matches exactly with this exponential function we just were looking at. 2 raised to the x. 0 folds, 1 rectangle. 1 fold, 2. 2 folds, 4 rectangles. 3 folds, 8 rectangles. 4 folds, 16. 5 folds, 32, right? So the function for this is 2 raised to the x power. So how many rectangles would I have? I'm curious. How many rectangles would I have if I could fold it 15 times? Can you figure that out for me on your calculator? If I could fold this 15 times, I'll try and fold it 15 times while you try and use your calculator to figure out what the answer would be. So 1, 2, 3, 4, 5, 6. Shit, I can't go past, I don't think I can go past 6. 7, it's too hard. But if I could physically do it, how many rectangles would I expect to see? So does anyone have it?
I think so. Would it be 225?
I think you did 2 times 50. No, what did you do?
What was
Did
I
you
supposed
use,
to do?
you should go 2 raised to the 15th power on your calculator.
2 to the 15th power?
Yeah, what did you say, 225?
Oh, yeah, I was
think
off.
you
I
did it
did
the other way
15 to the
around.
second. Okay, so then you
Yeah,
get like,
try it again.
sir, I don't know if you could have ever folded that much. It's like 32,768.
768, exactly. Yeah, I don't know. Have y'all ever heard of a show that used to be on the Discovery Channel called Mythbusters? It's an older show, but I don't even think they make episodes anymore. There's a thought that this experiment of folding paper, that there's a maximum number of folds that you can physically do. And I think on that episode, they proved that they could only do 13 folds. And what they did is they had this huge piece of paper in an aircraft hangar, and they folded it over, and they actually had a steamroller, one of those construction steamrollers, and they'd roll it over the paper to flatten it, and then they'd fold it again, fold it again. Let's see if we can find it. That'll be fun. Mythbusters folding paper. Let's see if we can find that. Here we go.
Back over at NASA, our team is finding out that folding a football field sized piece of
You see
paper
what they're doing there?
isn't exactly a breeze.
Y'all can't hear that, right? You could hear it, them talking? Oh,
But they managed to rein in the billowing parachute without any tears for an official fold 1.
Let it fall. Pull the slack.
okay, we're not gonna watch the whole thing.
8.
8
It sure
folds.
feels satisfying to beat up
That is a pancake.
as smooth as rolled dough. It folds back easy as pop.
9.
To achieve
9 folds.
growth, the paper is now 1,024 layers thick. It takes every ounce of strength they have to bend it.
You got it? That feels like an honest 11 to me. Nice. Yeah. 11.
Not only did they bust 7 folds, they turned it up all the way to 11.
So they got it to 11. I don't remember if they
Definitely
go
put this
past
on
that.
the bed.
Busted a move. And we're gonna go home before the sun completely goes.
Okay, so anyway, they got it to 11. I think they got to 11. They had to stop. They couldn't fold it another time. So there is a physical idea behind that. Okay, so think about what would 11 folds be? If you could do 11 folds, 2 to the 11th on your calculator should be 2048. So I want you to think about it this way. If I have 0 folds, I have 1 rectangle, don't I? But it's also 1 page thick. With no folds, just 1 page. If I fold it 1 time, how thick is this? How many pages thick is this with 1 fold? Right? The thickness of this. I have 1 page, I fold it over, now it's 2 pages thick, isn't it? If I fold it a 3rd time, it's now 8 pages thick. If I fold it a 4th time, I'm 16 pages thick. So when you get to 11 folds, that's 2,048 pages thick. To get to 15 folds, it would be 32,768 pages thick. It starts to become so thick you can't fold it on itself, right? So anyway, okay, we're going off topic here. I'm just trying to get you to see a physical example of an exponential function. Let's do another example of an exponential function, not this one, something different. Okay, so how about bacteria growth? So I'm gonna do, let's see, bacteria, Petri dish. So in a chemistry class, you can do this. You can get this sterile dish, okay, and you can, like, I don't know, go swab your remote control for your TV, right? Just take a little Q-tip and swab it, and just swab the inside of this dish and close it, and come back a few days later and see what's growing in there. So it takes the bacteria off of things that we touch every day, and then just put it in there and see what happens. And so a Petri dish, what you have is you start basically with bacteria, and then after time, it starts to grow in there. And most bacteria grow exponentially. So I'm going to give you an example. A certain bacteria triples itself every day. Find the function for this bacteria growth. Okay, so I want us to think about this visually, all right? I'm going to start with one bacteria. Here's the bacteria right here. It's a little microscopic bacteria. Now I'm going to give it a little smiley face. There it is. One happy little bacteria, okay? After one day, how many bacteria are there? After one day goes by, how many are there now? It says here it will triple itself every day, right? So after one day, it breaks up and becomes 3 bacteria. They're all happy too. How many are there on the second day? So this from here to here was 1 day. 1 day later, okay, how many will be there?
Wouldn't there be 9?
9. So how are you getting that? This one triples, right? This one splits into 3, right? This one splits into 3. And this one splits into 3. So now you have 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm going to go on the side here and make a T table. This is the day. This is the bacteria. At day 0, which is when the experiment started, we had 1 bacteria. 1 day later, we had 3. 2 days later, we had 9. How many will we have on the next day? Each one of those triples now. So what will it be? How many is that? So it's tripling each day times 3 times 3. Next one would be?
Would it be 27?
27. We'd have 27 bacteria. How many would be there after a week? So what would happen 7 days later? Well, to do that, we could keep on, we could figure out what happens at 4 and 5 and 6, right? But what's the function? What's the function? It's f of x. This time you see it's tripling each day. In the previous example, it was doubling each day, right? And we used, since it was doubling each, or it was doubling on each step, we used 2 to the x. What do you think we'll be using here? Instead of 2 to the x, what do you think we'll have?
Is it 3 to the x?
3 to the x, yep, 3 raised to the x. That is the function that describes this bacteria's growth. So get your calculator out and figure out what 3 raised to the 7 would be. How many bacteria are there after a week? 2187. How about after 14 days, 2 weeks? 3 to the 14th power. 4782969. That's 4,782,969 bacteria 2 weeks later. Starting out with 1, it grows very rapidly to this amount. Do you get the idea that exponential growth has to do with this idea of multiplying by a certain amount on each successive step, right? You could have doubling, which was the folding paper, that's 2 to the x. We could have a bacteria, which is 3 to the x. Understand? What would the graph of these look like? Let's take a look at this function f of x. Let's go to the 2 to the x one. If I asked you to graph this, we know if you plug in 0, you get 1. If you plug in 1, you get 2. If we plug in 2, we get 4. 3, we get 8. 4, we get 16. If we were asked to graph this, here's what it would look like. If we plug in 0, we get 1. Plug in 1, we get 2. Plug in 2, we get 4. Plug in 3, we get 8. And then we get 16. So 8, 9, 10, 11, 12, 13, 14, 15, 16 right here. And it looks like this. It's definitely not a line. It kind of looks like a parabola a little bit, right? Kind of looks like a parabola. So now I want you to do something on your calculator. I'm going to take a 2-minute break because something came to my door. But I want to ask you now, don't think about it as rectangles or anything else. Just look at it as a function. I'd like to see if on your calculator, you can tell me whether or not you can get an answer if we plug in negative numbers. So what would happen if you plug in -1, -2, -3, go to -4, do that on your calculator. We're using this function 2 to the x, see what answers you get. I'll be right back. Okay, did somebody get something for -1? You're doing 2 raised to the -1 on your calculator.
0.5.
0.5, 0.5, good. All right, how about -2? Did you get something for -2?
0.25.
0.25. Let's keep going. 2 to the -3.
0.125.
0.125. One more.
0.0625.
All right, so what's happening here? As we're going to the left and plugging points in, if we plug in -1, we're getting 0.5 or half, which is here. If we plug in -2, we get half of that, which is even smaller. And we plug in -3, even smaller. -4, even smaller. Oh, come on, stop. What does it look like we have? Does it look familiar? Are we ever going to get to 0 here? Try a big negative number. Try -10 on your calculator. 2 to the -10. You should get a really small number like 0.00000, but it'll be a positive number. So what we have going out this way is it's getting closer and closer, never gets there. Sorry, it looks like it does. It just keeps on getting closer. That looks like a horizontal asymptote from a rational function, doesn't it? Like a magnet that pulls it. This is the graph of f of x equals 2 to the x. That's the graph. What I'd like for you to see now, I'm going to go to my graphing software. I'm going to have the computer graph 2 to the x. There's 2 to the x. There it is. So it's not a parabola, right? It's not a line. It's not a parabola. It's not a polynomial. Remember, polynomials do this nice up and down, and it's not a rational function. Let's look at 3 raised to the x. There's 3 raised to the x. Notice they have some similar characteristics. They both have the point 0.01. They both have this horizontal asymptote. They're getting closer and closer to 0 over here. But on the right-hand side, notice that the blue one grows faster than the red one. 3 to the x grows faster than 2 to the x. I could do another number like, how about 10 to the x? Oops, to the x. That's this green one. Again, it goes through the point 0.01, gets flat here, but notice it grows faster. It's above the blue one and the red one. So the bigger the number is on the bottom, the faster it grows. Now you hear about this on the news all the time. Just turn on the TV and you'll hear, watch a TV show and you'll hear people say, oh, it's growing exponential or it's exponential growth. You hear it all the time. What they usually mean is it's really fast growth, really, really rapid growth. I think the bacteria is a good example of how fast things grow. COVID, right? You think about COVID and the whole thing about social distancing and all that. Why is that so important? And I'm not here to debate COVID. I'm just saying any virus that's transmitted from person to person. If you have one person and they go out to eat, right? And they're in contact with, with 3 people, and they infect those 3 people with whatever they have. And then those people go home, this person goes and visits their 2 friends. They go home to their family, and this person goes and visits someone, right? Now you've got more, right? And then what happens is exponential growth. It's exponential, almost like the bacteria. So you get one person on an airplane, right? Transmits something to several people. They all go to their families. That's all exponential growth. It's not linear, it's not quadratic, it's not a polynomial, it's exponential. So these functions come into play a lot in the real world, all right? So what I'd like to do now is I would just like to give you the general definition, all right, of an exponential function. In general, an exponential function of base A, okay, an exponential function of base A is the way we'll say this, is f of x equals a raised to the x, where a is a positive number and a is not equal to 1. So what I'm saying to you here is that there are an infinite number of exponential functions. Examples that I've given you are like f of x equals 2 to the x. That's an example. In this example, a is 2. F of x equals 3 to the x. That's the bacteria. Here, a is 3. You can do any exponential function as long as the base, that a, as long as that number is a positive number and it's not 1, then it's an exponential function. So here's another example that I haven't given you. This is an exponential function, 1/2 raised to the x. Here, the base is a half. 1/2 is a positive number, and it's not 1. So this qualifies as an exponential function. I wonder what this looks like. I mean, we know what this looks like, right? 2 to the x, we graphed it. 3 to the x, we graphed it. I wonder what 1/2 to the x looks like if you graph it. Let me show you. Get rid of this one. Here's, you're looking right here, that's 2 to the x and 3 to the x. If I do 1/2 raised to the x, that's what it looks like. It's this one right here. Do y'all see that all it is like a reflection over the y-axis? It flips over. So now you have a horizontal asymptote out the right side, and the left side, it grows. So in general, when you're looking at exponential functions, you have two cases. If the a is bigger than 1, your graph must look like this. And it must go through the point 0, 1. All of them do. This is called exponential growth. That's what you hear about on the news. And then if the a is less than 1, like a fraction, like 1/2, then what you're going to have is it goes the other way like this. Still goes through 0, 1, and this is called exponential decay. So the way to tell the difference between exponential growth and decay is purely what the a is. The a tells you everything you need to know. All right, so what am I going to want you to do? Right? What is it that I'm going to want you to do on a test with exponentials? We already saw how hard it is to graph rational functions, right? This is tough. Like, there's a lot to do here, right? I have good news with exponential functions. You're going to need to be able to graph them, but it's going to be probably one of the easiest things to do out of all the things we've learned to graph. So here's what I want you to be able to do. I give you a function, f of x equals, let's do 4 to the x. And I'm going to ask you to sketch it now. Okay. Here's what you're going to do. All right. Everybody in the class is going to do this the exact same way. You're going to make a t-table. Here you're going to have x, and here you're going to have 4 to the x. And you're going to plug in some numbers. And everybody's going to use the same numbers. We're all going to plug in 0. We're going to plug in 1, 2, and 3. And we're also going to plug in -1, -2, and -3. 7 numbers that you're going to plug into that function. You're going to use your calculator. You're going to get the answers. So I'm going to get on my calculator and I'm going to figure out what these are. So 4 to the -3, 4 to the -2, 4 to the -1, 4 to the 0, 4 to the 1, 4 squared, 4 cubed. So this one I get 0.0156. Here I get 0.0625. By the way, is this sketch going to be exponential growth or decay? Is this growth or decay? I'm sorry?
Growth.
Growth, because A is 4, right? The base is 4. That's bigger than 1. This should be growth when we graph it. 4, 16, 64. So now what you do is you go over to a graph. And you're going to start plotting the points. So I'm going to start at 0, 1. I know that this point's here. I know when I plug in 1, I get 4. I know when I plug in 2, I get 16. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And now when I plug in 3, it's 64, which is off my graph, right? I'm not going to be able to get that point on here. So all I want you to do is connect these dots, draw an arrow, and then to the left, just have it flatten out to a horizontal asymptote. And that is it. That's all I want you to be able to do. All right, everyone make the same t-table. What I'm going to be looking for is, do you have all those things right? And then is your graph the correct growth or decay? And that's all. Okay, you think you can handle that? Is that better than rational functions? Better than this? Right? A lot less to do. I get this sense that y'all are all like ready for this summer to be over. I'm getting this feeling like a lot of you have run out of gas. No?
That would be the correct feeling.
Okay. I understand. We're almost there. We're a week away from the final. So let's do this. Let me give you one. Okay, let me give you 2. I'll give you 2 problems. See if you can do these. All right. So I want you on your own right now to see if you can sketch these. F of x equals, try 0.8 to the x. And then I want you to do 2.5 to the x. Now don't freak out because I've given you decimals. You're going to be using your calculator anyway. But you should be able to tell me by looking at these right now what A is, right? This is A and this is A. This one should be decay, exponential decay, because that number is smaller than 1, and this one should be growth. So for each one of those 2 different problems, set up your table, use the numbers 0, 1, -1, 2, -2, 3, -3, and see if you can come up with your tables and then draw little graphs. All right, let's take, I don't know, 7, 8 minutes to do that. This is really an exercise in calculator, okay? So on the test, you're gonna need to be able to use your calculator to get these answers. So now's a good time to work out any issues you might have, all right? Ask questions if you need help on how to use your calculator. Okay, I'm going to start filling in these values and then you check to see if you got them. All right, did anybody have any problems getting those values or have any questions about these? Using your calculator, what keys to press or anything? Now's the time. Go ready for a graph? Let's take a look and see if we can't find what these graphs look like. So for the first one over here, because this is 0.8, a is less than 1, we know it's going to look like this. Okay, it's going to be exponential decay. But let's go ahead and plot the points. So of course, when I plug in 0, I get 1. Let me do the positive ones first. When I plug in 1, I get 0.8, and then 0.6, and then 0.5. So it's getting smaller, so I can tell it's going to be decaying here. If I plug in -1, I get 1.25. If I plug in -2, I get 1.5. And I plug in -3, I get 1.95. So it doesn't look like it. It almost looks like a line, but it is growing this way. And it is going down, decaying the other way. So that's what I would want. If I asked you to do this on a test, this is what I'm looking for. On the other graph, we plug in 0, we get 1. Plug in 1, we get 2.5. We plug in 2, we get 6.5. So 3, 4, 5, 6, 6.25, somewhere around there. I'm just kind of ballparking these. It doesn't have to be perfect. And then 3, I'm way up at 15, somewhere way up here. And then to the left, I should have decay. So again, you don't have to be perfect with this. What I want you to do is just make sure you have the correct general shape of the graph and that your table is correct. Okay, any questions? All right, so let's move on. We still have a little bit more I want to do today. Now, when it comes to exponential functions, right? When it comes to exponential functions, the base here, I said A, just has to be a positive number and it cannot be equal to 1. Those are the conditions that we have on A. There is a very, very special base that is used throughout mathematics. It's a very special number that, well, it's so special we have a special name for it, okay? And it is when you let A be equal to about 2.718. It actually keeps going and going. This number right here, 2.718, is a very special number. So special, in fact, that we have a special symbol for it. It's the number what we call E. Have you all heard of pi before? Right? You've heard of pi like for finding areas of circles, right? You've heard that at some point. Some of you may know that pi is about 3.1415. It's this very special number. It's so special that we give it a symbol, pi. Well, E is exactly the same. E is this really special number. It's about 2.718, and it's used a lot in math. And so if we define a function, f of x, to be that number, 2.718, raised to the x, we will write that e to the x instead. And this is what's called the natural exponential function. I'm not going to get into why it's called the natural exponential function, other than to tell you that we were looking for a function that behaved a certain way, and this turns out to be the only function that behaves this certain way. The behavior is something that we talk about in calculus. It's not something you need to worry about here, all right? You just need to know that this is a very special function. And so if I asked you to graph it, can somebody tell me, would this be exponential growth or decay?
Growth.
Growth, because the E is actually 2.718. It's bigger than 1, right? So we should expect growth here. So if we were to graph this, we would need to make our table. And then we would need to do this on our calculator. So on your calculator, you should have an E key. Okay, everyone needs to find that E key on their calculator. And you need to figure out what e to the -3 is, e to the -2, e to the -1, e to the 0, e to the 1, e squared, and e cubed. You need to figure out what those are. So take a minute, see if you can match up with my answers. I'm going to do this on my calculator right now.
I have a question.
Yes.
So anytime we use e, it'll always be followed by an exponent?
You can have e just by itself as a number. I mean, e is just a number. That's all it is. Okay. But if we use that number as our base, then what we have is the exponential function, the natural exponential function. Just like the number 2 by itself is the number 2, right? But if I say 2 raised to the x, now we're talking about an exponential function.
Okay.
E by itself is a number, but if you raise it to the x, we have this very special exponential function. I don't know if I'm answering your question.
No, I think you did. I understand.
Okay. So get on your calculator, see if you can do e to the -3 and see if you get 0.0497. And then try e squared, or e to the -2. You should get 0.135. I'm just rounding these like 3 decimal places, 4 decimal places. E to the -1. 0.367, e to the 0 is 1, e to the 1 is 2.718, e squared, 7.389 or 39, and e cubed, about 20.09. So please confirm that you can get these on your calculator. I'm not going to graph it. All I'm going to tell you is just remember, this should be exponential growth. So the graph should look like this. I'm not going to go through and do it. Okay. So again, this part of today is about exponential functions. Exponential functions are some number raised to the x power. If that number is bigger than 1, we got exponential growth. If it's less than 1, we have exponential decay. We can have any number we want as the base, as long as it's positive. If we use e as our base, we get this very special natural exponential function. Now, where would we ever see this used? I'm going to give us, now we're going to move into some applications. Simple interest. Okay, simple interest. So what is simple interest? So let's say that you go, I don't know, I'm sure many of you have credit cards, right? So when you have a credit card, then you're basically borrowing money from the bank, right? The bank is saying, hey, go ahead, go buy something, go buy the new, whatever, iPhone or whatever you want to do. And then you're borrowing money from us. And what you need to do is pay that money back. And you'll pay that money back plus interest. And the interest is basically where they make their money, because they're going to say, oh, we'll lend you $2,000, but you're going to owe us that plus a certain percentage. And that's what simple interest is. It's a way that we can calculate how much money we would owe. So that's the credit card example. Another example would be let's say you get paid and you've got your money, from your job, and you put it in the bank. The bank will actually pay you to hold on to your money. So it's kind of interesting the way banks work. You have a bank, right? There's your bank. And you got people over here who want to borrow money with credit cards or however they want to borrow money. And you have people over here, right? These people are going to lend their money to the bank, right? So when you go and you put your paycheck into the bank, you're putting your money in, right? And then the bank is actually turning around and giving that money to other people. The thing is, the people who are borrowing, like on the credit card, they have to pay back a lot more than what they borrowed. Does anyone know what the interest rate is on credit cards? Anyone have any idea of what the interest rate is? Common? What's the average credit card interest rate in 2021? Let's see. Here we go. National average 16.16. 16.16%. An easy way you can kind of wrap your head around this is that if you borrowed $100, okay, if you borrow $100, they're going to want $100 plus 16% back. So for every $100 you borrow, they want about 116 back from you. So for every $100 you borrow, they're going to make $16 off of you, if that makes sense. Very, very high interest rate. On the other hand, these people are putting their money in the bank, and the bank is saying, okay, we're going to give you money. Thank you for letting us use your money. We're going to give you money to use your money. So what is the, let's do average checking account interest rate. So if you put your money into a checking account, is that a typo? The average bank interest rate checking accounts in the United States is 0.03%. That's not a typo. 0.03%. That's not even 1%. In other words, if you give your money to the bank, yes, you will make money off of that, but it's not much. That's like 3 pennies for every $100. So for every $100 you put into the bank will give you 3 cents for that. Yet they're loaning that money and charging someone $16. So do you see how they're making their money? How the bank makes their money? They make $16 off of this person and give you 3 cents of it over here. So they make, $15.97 roughly. All right. Y'all seem somewhat not interested in this, but this is, money. So I thought it might be interesting to you. If I'm going to advise you on anything. I'm not a financial advisor. Try and stay away from credit cards, okay? If you're gonna use them, make sure you pay off your balance every month. Don't carry a balance. A lot of Americans rely on credit cards to go from month to month, okay? It's a very dangerous place to be. I understand you got to make ends meet, but try and stay away from credit cards. I have like 6 credit cards, I think. And all of them have a zero balance. And I take advantage of the fact that if you use credit cards, a lot of times they'll give you perks for it. Like, you know, they'll give you 3% back if you buying gas or something like that. So I use that, but every month I pay it off. Like I have zero balance. Okay, so what are we gonna do? Simple interest. There's a formula, all right, for simple interest. I'm gonna give you the formula and then we're gonna do a problem. So here's the formula. A equals P times E, yes, that's the E we were just talking about, raised to the R times T. That is your simple interest formula. Now, I need to explain what all these letters are. First of all, P is the amount of money you start with. So that P, actually it's called P because in bank terminology or financial terminology, P stands for principal, which is the original amount. So this might be the amount that you borrow initially. You go buy that, you know, whatever, that $2,000 computer, your P would be 2,000. R here is the interest rate. And you want to always, when you're using the formula, you want to convert it to a decimal. T is time, and that's measured in years. So you have P in the formula, which is the amount you're going to start with. The R up here is the interest rate. The T is the time period that we're talking about. And the last thing is, what's the A? The A is the amount after T years. Now you might be asking, well, what's the E? Well, the E I already told you is the button on the calculator. Okay, so that is not something we need to worry about. It's just part of the formula. So let me show you how this works. Okay, and I'm going to take a pretty cool example. I think it's, let's say that you win the lottery. Okay, let's say you win the lottery. You win. How much do y'all want to win? Caitlin, how much do you want to win on this lottery?
Can I just say any amount?
How much?
$1 million?
1 million? Okay, you win $1 million lottery. Okay, now let's say that's after taxes, because when you win the lottery, the government comes in and takes about half of it away. Okay, so let's say you walk away with $1 million. Okay, you win $1 million lottery. You place that money into a simple interest account at, let's do an interest rate here. I'm going to do something kind of high, but we're just going to put it in there and we're going to lock it away. We're not going to touch it for 5 years. Okay, we're just going to put the money into an account. Let's say the interest, simple interest account at, let's go with, let's look up real things. CD rates, 5 years. So a CD is something you can get. A CD is something that you can get from a bank. where it's called a CD stands for not compact disc. It stands for certificate of deposit, which just means you are going to give the bank your money and you promise not to come back and try and get any of it back from them for a certain amount of time. You can say, hey, here's my money. You can have it for 1 year. I won't even ask for it. Or you can do 2 years or 3 years or 5 years or even longer. And so let's say that we're going to take that money and we're going to put it into account. Right now, the interest rates are pretty crappy, 1.15. Let's go with that one. Okay, at 1.15% for 5 years. How much money would you have after that 5 years is over? So you're going to put the money into the account for 5 years. The bank is going to pay an interest rate of 1.15%. I want to know how much money you'll have at the end of that 5 years. So here we go. You ready? The amount that we will have will be equal to the principal. What's the principal? The amount we started with, right? So that's how much we won in the lottery. That's $1 million. Times E raised to the R. Now, R is our interest rate. Keep in mind, this interest rate, we have to take that and convert it to a decimal. So when you convert that to a decimal, you have to move the decimal point 2 places to the left. So it becomes 0.0115. So I put that here, 0.0115. And I need to multiply that times T, which is the time, 5 years. So we have T is 5, the interest rate, right? And then we have the principal right there. Everyone understand? So this should be equal to $1 million E. Now what I'm going to do is on my calculator, I'm actually going to do this calculation. I'm going to do 0.0115 times 5, which gives me 0.0575. And then very, very careful here. You have to do this on your calculator now. What is E raised to that number? So I do E raised to the 0.0575. And I get times, let's see, 1.05919. And then I multiply that times 1 million. So I get 1.05919. Let's see here. Hold on a second. There we go. 1059185.30. All right. Can somebody interpret what this answer means to us? Someone tell me, like, what happened in the 5 years?
Isn't it that like because you weren't like touching it and it had an entrance, okay, Caitlin.
Interest, yeah.
Interest, that the amount grew.
It grew, yeah. How much did it grow by? We started with $1 million, and 5 years later, how much do we have?
Oh gosh, the 59,000. Is that right?
What does it look like to y'all? We started with $1 million, and now we have $1,059,185. So we've gained $59,185.30. That's how much we've gained, right? Does that make sense, everyone? That's our gain. Now in 5 years, right? That's in 5 years. So how much did we gain every year? Let's just take that answer and divide it by 5. We gained it's about $11,837 per year. Okay. So if you won $1 million and you just put it into this sort of bank in a CD, you're gonna earn almost $12,000 a year on that money for just letting it sit there. Okay, that's not that great. If you invest that money into the stock market instead, let's see what the average stock market return is over the last 30 years. So on average in the stock market, your growth is about 9.885% over the last 30 years. So if we were to do the same problem, but I changed this to, let's say, 10% instead of this, let's say we change it to 10%, then our formula would become A equals 1 million, one more zero, e to the, now 10% converted to a decimal would be 0.1 times 5, which would be 1 million. I'm going fast because I'm almost out of time. E to the 0.5. I do this on my calculator. Ready for this? 1,648,721.30. Look at the difference between that. If you did the stock market instead of the bank and got back the average return on the stock market over the last 30 years, which is about 10%, look at how much money you will have after 5 years. 1,648,721. That means you gained $648,721 gain. That's your gain. If we divide that by 5, that's about 130,000 a year. Compared to 12,000 or whatever it was, which means that if you're willing to take a higher risk, because the stock market's risky, you may not gain back 10%. You may lose money. But if you're willing to take that bigger gamble, you have potential of a bigger return. In fact, I would argue that many of y'all are in school and would be happy to come out of school and get a job paying you $130,000 a year, right? If you had that much money to start with, $1 million to start with, and you invest it properly, you could basically live off of your interest. This is why people that start with a lot of wealth can continue to be wealthy, because their money continues to gain interest for them, right? So think about people like, that are billionaires, right? They invest their money in different places. They get returns. They're making, tens of millions, hundreds of millions of dollars just off of their money. Their money just sitting there is making them more rich. So yeah, it'd be nice to win that lottery. The worst thing you could do is win the lottery and go blow it all, okay? Because it's hard to build that foundation of money to earn money off of your own money. So people win lotteries, they go blow it all, and then they don't have anything left. So, okay, we're out of time. What I want to do is I want to give you some problems to work on. And then what we're going to do next week is we're just going to review for the final, okay? Because we have to go back and look from the beginning of class to where we are now, and we're just going to review for the final. I might introduce a few more topics. I'm going to go over some more of this, but Monday will be basically getting us ready to make sure, and expect to see a review for the final. I'll send it out here in the next couple of days, right? That way you can start working on it over the weekend.
So we're skipping the test 4.
Oh yeah, no, yeah, last time I said that. Yep.
Okay.
Yeah. In fact, you know what? Forget me giving you problems right now. I'll do that when I send you the review that'll have problems. I'll tell you which problems are kind of the new problems from today's lecture. All right. Everyone have a good weekend. If there are any questions, I'll hang out.
Thank you. Have a good weekend.
You too.
Thank you.
Thank you.